Hello everyone. Earlier we talked about the no-load operation of transformers. Starting today, we will analyze the load operation of transformers. The steps of analysis will still follow electromagnetic relationships to basic equations to equivalent circuits to Phasor diagrams. These four sections for explanation. Today, let's first look at single-phase transformers on the load operation, physical conditions, and basic equations. First, let's look at the physical conditions during the load operation of transformers. Physical conditions, that is, what is called the load operation of transformers. The primary winding of the transformer is connected to an AC power source with a rated frequency and a rated voltage. The secondary winding is connected to a load. This operating state is called the transformer's load operation. Transformers. The principle of load operation is illustrated in the diagram, as shown. The transformer, primary side connected to the rated voltage U1, producing primary current I0, forming the main magnetic flux phi m, forming the primary leakage flux phi 1 sigma on the primary side, producing induced electromotive force E1, and the secondary side, producing induced electromotive force E2, and producing primary leakage induced electromotive force E1 sigma. This is also what we mentioned earlier. No-load process, when the secondary winding is connected to a load. On the secondary side, under the influence of the induced electromotive force E2, the secondary winding has current I2 flowing through it, but due to the power voltage U1 and the frequency F remaining unchanged, thus the main magnetic flux remains unchanged. When the magnetic force on the secondary side appears, the primary current must change from I0 to I1. At the same time, producing secondary leakage flux phi 2 sigma, producing secondary leakage induced electromotive force E2 sigma. The primary magnetic force F1 on one hand produces the main magnetic flux phi m. On the other hand, to counteract the influence of the secondary magnetic force F2 to maintain the main magnetic flux unchanged. At this time, the transformer is in a new electromagnetic balance state. This is also the transformer's load operation process. During load operation, the electromagnetic relationships between various physical quantities, as shown in the diagram. During the load operation of the transformer, the secondary side has current I2 flowing through it, producing secondary magnetic force F2. This magnetic force also acts on the main magnetic circuit of the core. According to Lenz's law, the effect of F2 on the main magnetic field is to attempt to change the main magnetic flux phi m, since the power voltage U1 remains unchanged. The main magnetic flux phi m can be considered basically unchanged. Thus, when F2 is present, the current flowing through the primary side must change from the no-load current I0 to I1. The magnetic force changes from the no-load F0 to F1. The primary side, the added part magnetic force, is used to counteract the secondary magnetic force F2 to maintain phi m unchanged. At this time, the physical quantities of various parts of the transformer have established a new balance relationship. During load operation, the main magnetic flux phi m is actually produced by the combined magnetic forces F1 and F2. Simultaneously, F1 and F2 in the primary winding and in the secondary winding, respectively, produce leakage flux phi 1 sigma and phi 2 sigma, and in their respective windings, respectively produce leakage flux induced electromotive force E1 sigma and E2 sigma. Additionally, the primary and secondary windings current I1 and I2 will also produce voltage drops in their respective windings resistances, I1R and I2R. Earlier, we talked about transformers under load operation, physical conditions. Next, let's look at the basic equations. First, let's look at the magnetic force balance equation. The transformer during the transformation of electrical energy, neglecting the internal losses of the transformer. The primary and secondary electrical power are basically equal. When the primary and secondary voltages are not equal, the currents on both sides are inevitably different. The current on the high voltage side is small. The current on the low voltage side is large. Therefore, the transformer changes the AC current while transforming the AC voltage. The transformer from no-load operation to load operation, the power voltage remains unchanged. The main magnetic flux remains basically unchanged. Therefore, the synthetic magnetic force during load operation is basically equal to the no-load magnetic force. F1 plus F2 equals to F0, or N1 times I1 plus N2 times I2 equals to N1 times I0. Expressed in terms of current, I1 plus 1 divided by K times I2 equals to I0. I1 equals to I0 plus left bracket minus I2 divided by K right bracket equals to I0 plus I1L. From no-load to load, the primary winding current I1 as a component I1L to balance the effect of the secondary winding. Therefore, during load operation, the current of the primary winding contains two components. One excitation component I0 used to produce the main magnetic flux. The other is the load component I1L, used to balance the effect of the secondary winding. Magnetic force, the primary and secondary currents establish a dynamic balance, jointly produce the main magnetic flux, called the magnetic force balance. The primary winding absorbs power from the grid and transfers it to the secondary winding. The secondary winding current increases or decreases, causing the primary current to increase or decrease. The absorbed power also increases or decreases. During load operation, neglecting the no-load current, I1 approximately equals to minus I2 divided by K, or I1 divided by I2 approximately equals to 1 divided by K equals to N2 divided by N1. It shows that the primary and secondary currents are approximately inversed proportional to the turns ratio. It can be seen that different turns can change not only the voltage, but also the current. Let's look at the electromotive force balance equation. According to the electrical engineering, Kirchhoff's voltage law, we can write the primary and secondary electromotive force balance equation. Primary side, U1 equals to minus U1 plus I1 times R1 plus J times I1 times X1 equals to minus E1 plus I1 times Z1. Secondary side, U2 equals to E2 minus I2 times R2 minus J times I2 times X2 equals to E2 minus I2 times Z2. Current relationship, I1 equals to I0 plus left bracket minus I2 divided by K right bracket. Transformation ratio, K equals to E1 divided by E2. Excitation, minus E1 equals to I0 times Zm equals to I0 times left bracket Rm plus J times Xm right bracket. Load, U2 equals to I2 times ZL. This is the transformer in steady state operation. The 6 basic equations, various electromagnetic quantities, simultaneously satisfy U1, K, Z1, Z2, Zm. These 6 equations using U1, K, Z1, Z2, Zm, Zl to solve for I1, I2, U2. But for general power transformers, the transformation ratio K is relatively large, making the primary side and secondary side voltages the magnitudes of currents also large, making calculations inconvenient and drawing phasor diagrams even more difficult. Therefore, in the next class, we will introduce and analyze the transformers, an important method. Equivalent circuits. That's all for today's class. Class dismissed. Thank you for watching.